So we're just picking up right where we left off. We were here. We just did number one. Took a little time. Moving on now, and I'm back on the lecture document. So we're going to page 3, describing quantitative data. Already, we're done with categorical. This is all you can do: bar graphs and pie charts. That's all you got for categorical data. So let me just kind of set this here. We'll come back to got a little bit more to read here in the lecture. So what do we have? Okay, so like categorical data, we are still interested in how the data is distributed. But now we don't have categories where how the data is distributed. We have numbers. How is this going to work? We can display this in several ways. A great way to begin is talking about the histogram. So by definition, it's rectangular bins of equal width drawn adjacent to one another. And you can see an example just below. And now that sure looks a lot like a bar graph, but now the bars are right up against one another. And we actually don't refer to them as bars here. We refer to them as bins. And notice they all have equal width. Well, that might be true in a bar graph as well. But now we're representing quantitative data, not categorical. So how does this work? How do we have these bars, but yet we're dealing with numerical data? Let me read some more. The vertical axis can be the frequency or relative frequency. Okay, so we can have just the regular frequency histogram, or we can have a relative frequency histogram. And I say this is the bar graph equivalent for quantitative data. Okay, so looking at the first graph there, in that same class from a couple of years ago, I asked them their birth year. And these are the results that I got. Okay, so I'll give you a moment just to look that over. Maybe pause the video. And typically what I do is ask the class, hey, just looking at that, without me describing anything, let me just ask, hey, how many students from that class were born somewhere between 1990 and 1995? How many students from that class were born between 1990 and 1995? And typically there's several people who raise their hand or just shout it out. There's five of the students from that class were born between 1990 and 1995. And we can see it there where you see 1990, the bar coming up kind of, to the right of 1990 would be all the people between 1990 and 1995. And then sometimes I'll ask, okay, how many people were born between 1995 and 2000? And it's a little bit harder to see, but I think it's about 24 students. So he doesn't make it quite all the way up to 25. And then the question becomes, hey, what if a student was born in 1995? Which bin would they land in? If they were born in 1995, would they land in the 1990 to 1995 bin? Or would they land in the 1995 to 2000 bin? And the answer is, for a histogram, if you land right on the border, then you always go to the next one up. So if someone was born in 1995, then we would place them in the 1995 to 2000 bin, the one that falls to the right or is above. Okay. So really, you could probably say, for that previous bin, that really represents 1990 to 1994. Because as soon as you hit 1995, then you're in the next one over. Okay. And then just below that, you see the relative frequency. So same idea, but now we have the proportions along the vertical axis, or you might think of them as the percentages, but all the same information. And that, that kind of gives a different take on it. So now we can look and say, yeah, over 50% of that class was born somewhere between 1995 and, 1999. Because as soon as you hit 2000, you'd go into that upper bin. Okay. One person rocking it from the early 1970s. So that was pretty cool. It gets, get a little more diversity there. Okay, let's get to practice problem number 2. So I'm giving you some data. It says below are the test scores of 450 psychology students placed into bins. The test was out of a possible 100 points. Okay, so there in that table, we see the bin interval and the bin frequency. So they've already divided these test takers up into bins of width 10. So you see that first bin is from 40 to 50. They might equal 40 in that bin, but as soon as they hit 50, then they go into the next bin. 50 less than or equal to x less than 60. And then as soon as you hit 60, you go into the bin after that. Okay, and we see the frequencies there on the right. Okay, so part A, create a histogram of the frequency. So we're just doing just a frequency histogram here, not bothering with the percentages. Okay, that's great. So it looks like all the hard work is done for us. They don't give us the raw data. It's already been organized quite a bit. We just need to create this this histogram. So I've gone ahead and set it up like so. So take a moment, maybe pause and draw this, and I'll explain what I did. So just like a bar graph, we've got a vertical and a horizontal axis. And you might have noticed even back in problem 1, it's common to write either frequency here or relative frequency, if that's what it is. Here it's frequency. Along the horizontal axis, notice I just go ahead and begin at 40. And, you know, that might seem like, well, shouldn't we start at 0? Well, you know, in statistics, you know, no, this isn't necessarily an XY plane. We're just trying to represent the data. It's okay. You don't have to start at 0 because the data begins at 40. So I'm just going to start it at 40 and then go every 10, right? 40, 50, 60, 70, 80, 90, up to 100. And then up the vertical axis. Now this one takes a little bit more thought. I'm going to look at the bin frequencies, and I need to identify the biggest bin frequency. And of course, that's 147. So I want to make sure that I'm able to capture 147. So let me just make it easy. Now this, we do need to start at 0 because we're talking about how many there are. So starting at 0 and going up to 150, that will be enough to capture everyone. Okay, and now we're going to draw it out together. So for that first bin, there were only 3 people that scored between 40 and 50. Makes sense. This thing's out of 100. Okay, so I'm going to go here and write, that's 10 the way I've drawn this. So 3 is way down here, and it's kind of difficult. It's so small. And I'm going to go ahead and shade that in. Okay. And then the next one, as soon as we hit 50, now we go to the next bin, and that is 10. So I'll go all the way up to 10 and then all the way over. Okay. And then from 60 to 70, it's 53. So go up to 50 and just a hair above 50. Do the best you can with that. And I'll shade that. And notice, of course, my bars are all riding one up, you know, right up against one another. They're touching. Okay, then as soon as we hit 70, we jump into the next bin. The 70 to 80 bin has 107. So now it's really jumping up almost to 110. Okay. Okay. And the 80 to 90 has, oh, there's the 147. So we're almost all the way up to 150. Just short of 150, just barely short. Okay, that'll work. That works right there. Okay, nice. And finally, 130 in the 90 to 100. So there it is. So, dude, you know, eyeballing it as best we can here. We're paying our dues. doing these histograms by hand. There you go. Okay. And I really like the idea, just the name that they give to these bins, right? Because it's almost like we're throwing. It's almost like these are like buckets, and as we throw more in, it's like it's stacking up. So 147 people, students, got thrown into this bin, and so it's stacked way up there, where very few people thrown into these lower bins. It's a good visual. Okay, part B. Um, if we sum the bin frequency values, what should it total? So this really isn't even talking about the histogram. It's just kind of getting us to think about the data and where it's coming from. So what's going on there? If we add up all of those bin frequencies, do we know what it should add up to without actually calculating it? I'll give you a moment. It'd be much more interesting if we were all in class together, but we're not. What should those total? How should we know what that should be without even actually adding them? And the answer is 450, because it said at the beginning of the problem, below are the test scores of 450 psychology students. Now, it maybe isn't a bad idea to check, but that should add up to 450 if everything is as it should be. Okay, hey, I think we're going to go ahead and move on to practice number 3. It says to study the great white shark, the lengths of 16 sharks were measured. Those lengths are in feet. And now we have some raw data again. We've got this table of the 16 great white shark measurements in feet. And thinking about that is a little scary. That first one there, 18.7 feet. And well, that's not the biggest one either. Okay. So then it asks us create a relative frequency histogram. All right, now we're going for it with relative frequency. Select a number of bins that appropriately depicts the distribution. All right. This one, they don't even tell us how many bins we should take, right? In at number 2, we had 1, 2, 3, 4, 5, 6 bins, and that seemed to show the distribution pretty well. But they don't tell us how many to use here in number 3. We're going to have to do that ourselves. Let's figure that out first, how many bins we need, because only then are we going to look back at the data and determine how many of these shark links go into each of the bins. So in number 3, that should be our first question. How many bins to create? Okay. Well, we're going to have to do this strategically. So let's find the shortest shark length, and let's find the longest shark length, and that will help us get started. So I'm just going to show you my work here. So if you look through that data, the shortest great white shark was 12.3 feet. I don't know about you, but 12.3 feet is pretty long. That is pretty long if you were in the water with that thing. All right, so maybe a good starting point then would be 12. We just go down to the next whole number. Okay, the longest shark there was 22.8 feet. That is ridiculous. Almost 23 feet long. That's longer than a car. Easily. All right, anyway, 22.8 feet. So maybe we start at 12, we end at 23. That makes sense. Now, what would that mean as far as the bins? Well, we can tell that 23 minus 12 is 11 units. You're like, wow, 11 units. What kind of options does that give us? Well, I guess we could make 11 bins, each 1 foot wide. 11's not that. It doesn't really lend itself well to choices, because you're kind of stuck if you want whole numbers, which we kind of like. Then 11 bins, each 1 foot wide. That seems like a lot of bins. And not very many sharks are going to end up in each one if we do that. Maybe we can have less bins than 11, but how? What would we do? Well, maybe starting at 12 is a good idea, but maybe we don't end at 23. Let me cross that off. Let me bump it up one. Let's end at 24. Okay, and now we have some options. So if you take 24 minus 12, well, then that's going to be 12 feet in total. Or 12 units. So if you have 12 units, then you've got some choices. You could make 6 bins each. 6 bins each 2 feet wide. That would give you the 12. We had 6 bins in the last example. Or you can make 4 bins each 3 feet wide. That doesn't seem too bad either. You could go even further and say 3 bins each 4 feet wide. But when you get down to 3 bins, you're kind of pushing it on the minimalist spectrum. I think 4 or 6 is going to give a better depiction of this data. I think 3 is, we're going to lose information, and if we do that, but we definitely don't want the other extreme being 11 either. I think given these two choices, and if we were in class, I'd give you guys the option, which one should we do? And whoever shouted out the loudest and the most confident, maybe we'd do that. But I think I'm going to have to choose, obviously. I'm going to go with the 6 bins, each 2 feet wide. I think that shows the data well. 4 would be a good choice as well. I like 4 bins, each 3 feet wide, but let's go with the 6. Okay, so if we go with the 6, I'll just show you my work here, and then we'll do the histogram on the next page. So here's what I've got. Here's our 6 bins and the intervals for each. So if we're starting at 12, we're going 12 to 14, and then 14 to 16, 16 to 18, 18 to 20, 20 to 22, 22 to 24. And now this is going to be kind of tedious again, but hey, that's just the way it goes. We got to go through that shark length data and count up how many sharks fall into each. So I've done this for us. If you feel so inclined, you can look back at that shark data and confirm my numbers here, but I got 3 fall into the 12 to 14 bin. Only 1 falls in the 14 to 16 bin. Let me try. That one was 15.8. It fell in here. Okay, in the 16 to 18 bin, there were 7, quite a few in that one. In the 18 to 20, there were 3, and then there was 1 in both the 20 to 22 and the 22 to 24. Now remember, when you are counting these up, we had these decimal values for all of ours, but if you should happen to count up data and you hit one of the boundaries, so for instance, maybe one of these sharks was exactly 14 feet long, which of the 2 bins would you place it in? And the answer is the upper one. If you hit the boundary, you go to the upper. Okay. So now what? Oh, if these are the frequencies, right? 317, 311, but we want the proportions for the relative frequency. So we're going to take, kind of like what we did in the bar graph earlier in the last video, we're going to take the frequency and divide it by the total. So if there were 3 here, divided by a total of 16 sharks. And we do that for each of these. So 3 over 16, 1 over 16, 7 over 16, 3 over 16, 1 over 16, 1 over 16. And we get these decimal values. I won't read those all. Hopefully you can see that all clear enough. Let me make sure my camera is nice and focused. I think that's about as good as it's going to get. All right. So with that in mind, maybe I'll try and keep that all on the screen. Now we're going to create our, no, I can't do it. All right, sorry. We're going to create our relative frequency histogram. So what I've done, I've gone ahead and set it up already. So we got our 2 axes. On the horizontal axis, I start at 12, 12, 14, 16, 18, 20, 22, 24. And on the vertical axis, I saw the biggest frequency was the 0.4375. So I want to make sure I can capture that one. So I went all the way up to 0.5, and then of course that's 0.1, 0.2, 0.3, 0.4. The way I chose to set it up. Okay, so let's do it as best we can by hand. So in the 12 to 14 category, it was 0.1875. So that's almost up to 0.2, something like that. And I like to shade these in myself personally. And then in the next category, there was only one shark. So that ended up being 0.0625. Well, there's 0.1, so 0.06 is a little bit over halfway. All right. Then we had the big one, 0.4375, so that's shooting way up. That's zero point 0.4, so 0.43 is a little bit past that. And we'll try and do this as best we can. A straight edge may be helpful. All right. The next one was back to 0.1875, so that's the same height right there. And then the last two were the 0.0625, so these are here and here just about, and I think that's a pretty good picture of the way these sharks, the lengths of these sharks are distributed. And a really nifty way to, it's almost like we're creating categories, right? So even though we have numerical data, we're kind of thinking like 12 to 14 is the first category. 14 to 16 is another category. So it's this clever way of creating categories out of numerical data. And there you go. Okay, let's stop this video here. More to come.